Okay, so we have looked at Bayes' rule in theory, and now what we're going to do is we're going to apply this Bayes' rule using the PDF version that I showed you last time with probability density functions, right, in a practical setting involving a binomial distribution, which is the familiar discrete random variable case that we saw in the beginning of this course. So let's think about this. Okay, we are talking about a data generative process. The data are coming from a binomial distribution, and so the likelihood function in this particular case would look like the output shown here for some particular value of the probability of success theta, right? And given 46 successes in 100 trials, for example, I would get this particular probability of getting 46 successes out of 100 trials, assuming that theta is 0.5, right? So in the likelihood function, remember, theta is always a variable, right? So we could write this likelihood function in the following way. We can drop the normalizing constant, right? As I've been discussing repeatedly, this normalizing constant is of secondary interest to us, right? What's interesting is the kernel of the distribution. So let me write out the kernel of the distribution in the binomial likelihood, which is theta to the power of 46 times 1 minus theta to the power of 54, right? So this term, this kernel, is now proportional to the likelihood that we had here because I've dropped the normalizing constant. Okay, so our goal is to get the posterior distribution of the parameter theta given the data that we have, given the 46 successes out of 100 that we have, right? So formally what we need is the posterior distribution of theta, which will be a continuous distribution, right, with a support 0 to 1. Why 0 to 1? Because it's a probability we are talking about, right? So the support of this distribution will be 0 to 1, right? And this can be calculated, the posterior distribution can be calculated up to proportionality, so ignoring the normalizing constants, by multiplying the likelihood, which we've got here, right, with the prior. Now, I said the prior, but I haven't actually defined the prior for theta. So that's what I'm going to do next, okay? So let's think about what kind of priors we might actually use for theta, right? Well, what do we need? We need a probability density function, right, that has a support going from 0 to 1, right? It should range from 0 to 1 because we're modeling a probability here. And it should allow us to represent our prior uncertainty about this theta parameter. That's the significance of the prior distribution, which I will, of course, unpack further in the coming lectures. The prior distribution is going to represent what we believe are plausible values of the parameter theta before we have even seen any data, right? Before we've seen the current data that we're trying to model, which is 46 successes out of 100, right? So this is that's why it's called the prior on the parameter theta. It's specified before actually looking at the data, right? Okay, so it turns out that in this probability distribution theory, the beta distribution is a very good candidate for using as a probability density function for the theta parameter, right? It really works very well. Why? Because it has a support that goes from 0 to 1. So what you're seeing here is the beta distribution specified. So for any value between 0 to 1, this is the term that the beta distribution will have for defining the probability density function. And for all other values outside this range, the value will be 0. Okay, so that's what the definition is of the beta probability density function, and we're going to use this beta density function for modeling our prior beliefs about the parameter theta, right? So one thing to notice about this probability density function is that it's defined in terms of two parameters. You know, just like the normal distribution was defined in terms of mu and sigma, the beta distribution is defined in terms of two parameters, which we'll call A and B. In different books, you'll see different terms like alpha and beta and so on, but they're the same thing, right? So we will write the beta distributions in terms of B, A, B. So whenever I write B, A, B, it means that I'm talking about a particular beta distribution with some parameters A and B, okay? All right, so in R, you will often see the DPQR family of functions for beta, right? So there in those functions, instead of a and b, R has the convention of writing shape 1 and shape 2. So shape 1 refers to A and shape 2 refers to the parameter B, right? So don't be confused about that, but when you're computing things in R, you will be using shape 1, shape 2 and not A and B, right? And just for your information, you don't need to use this information at all in this course, but the expectation and variance of a beta is defined by these equations here, okay? It's just good to know. It can be useful in some situations. Okay, so how do I decide what prior distribution to use for theta? That's the key question now, right? And what that means is I have to decide what those parameters A and B are, because those parameters will determine the shape of this beta distribution, which represents our beliefs about theta before we've seen any data, right? So how do we do this? Well, let's look at the parameters here, right? We can plot some beta densities. So I'm just using the d beta function, to plot these distributions. So you can see that the support ranges from 0 to 1. So this is a bounded distribution. There's nothing beyond 0 on the left side, nothing beyond 1 on the other side, right? And so what I'm doing is I'm varying the a and b parameters. And what this shows you is that when a and b is 1, you get the uniform distribution between 0 and 1. When I increase a and b to be the same values, but I increase the numbers, the distribution starts to get tighter and tighter and tighter. So what this means is that I can use my a and b parameter specifications to decide on how unsure I am about the plausible values of this parameter before I've seen the data. So it's a way to represent my prior uncertainty about theta. By specifying a and b, I can do that, right? So one way to interpret the a and b parameters is that you can think of a as a number of successes in some imaginary experiment and b as the number of failures in an imaginary experiment. So in this particular case, when a and b is 6, what you're really assuming is that the prior mean for theta is 0.5, because there are 6 successes and 6 failures, so 6 over 12 would be 0.5, right? So that's why this distribution is centered on 0.5. If I had a smaller number for A and a larger number for B, that means I would assume that the probability of successes is much lower, so then the distribution would skew to the left. So you can define different priors for theta distributions, depending on your prior beliefs. And later on I will talk about this a lot more, what it means to specify a prior, but right now we just want to understand the mechanics of this, right? Okay, so what we are now going to do, what I've just done, is I'm going to define some prior on the theta parameter, and what that will do is that it will allow me to, in this equation, it will allow me, in equation 2, to plug in a prior distribution here. I already know the likelihood, right? That's the binomial up to proportionality, okay? All right, so the obvious question to ask at this moment is like how should I decide what A and B are going to be? This is going to be a subjective move that I'm going to make, right? So what we are going to start with right now, just as starters, is we're going to assume that we don't have much prior information, right? So we could set A and B both to 1. In this case, we would have something called an uninformative prior. That's this uniform distribution that I'm showing you here. If, however, you have more prior information, for example, from previous research, right, on this particular problem, then you could define a prior that is more tightly distributed around whatever you think the true value is, right? But we will look at more examples about that later. But right now, this is a reasonable starting point. We just choose some reasonable priors for the parameters A and B for the prior theta, and then we will get an idea, of what the procedure is for calculating the posterior given the data and given a prior, okay? So what I'm going to do now, just for fun, I'm going to calculate the posterior distribution of theta using that equation 2 that I showed you earlier. I'm going to compute the posterior distribution of theta given 4 different priors. So I'm taking increasingly tight priors. Notice that as A and B increase, the distribution will get tighter and tighter. You should play with this and check that this is true, okay? So what you will notice is that we are getting more and more informative priors as we go down this list, okay? So what I'm going to do is I'm going to multiply the binomial likelihood up to proportionality with the prior distribution for the theta parameter, and I'm going to use 4 different priors, and I'll show you the 4 different posteriors that I get. Okay? So let's just plug it in. It's actually literally a simple multiplication involving no complicated mathematics. So the first time I saw this, I was pretty confused because it's surprising that you can just multiply 2 distributions. But what you're actually doing is that you're multiplying the mathematical form of the kernels of these 2 distributions. And the reason that we're using the beta distribution here is that it has the same form as the binomial distribution. So if you look here in this first equation 5, what you notice is that here is the likelihood term. Okay, so where is the likelihood? Yes, this one here, theta 46 times 1 minus theta 54. That was my likelihood term, right? The likelihood function. And what I've got here is my beta prior, just the kernel of the beta prior, okay, which is a beta 2 prior, just as an example. Okay, as I said, I'm trying out beta 2 here, right? And so how do I solve this equation? How do I multiply these 2 probabilities? It's just adding the exponents, right? Because I've got theta to the power of 46 here, and I've got theta to the power of 2 minus 1 here. So what is going to be the result of this multiplication? It's going to be theta to the power of 46 plus 2 minus 1, right? So that's how I end up with 48 minus 1 here. And similarly for 1 minus theta. I'm just adding up exponents. That's it. I'm not doing anything special here, right? And then I'm doing the same thing now for different priors. The likelihood remains unchanged, okay? This likelihood remains unchanged in all the 4 cases. What changes is this term here. I'm changing the prior specification, right? So the A and B values are 3 here, A and B is 6 here, A and B is 21 here, right? So you can see that the posterior can be trivially calculated, right? Up to proportionality, right? What we don't have is the normalizing constant, but as I said, we can always work that out, right? So, and that's really it. I mean, that's the whole story in a nutshell. That's how I'm going to use Bayes' rule to derive the posterior distribution, at least in this simple case, right? So we can now try to visualize what's happening when we have a particular prior, we have a particular likelihood, and we get a particular posterior, right? So this is the code that I'm going to use for this. I won't explain this code. You can look at it later, and it's also discussed in the lecture notes, okay, in the textbook. So you should look at that later on. But what I want to show you is the result of this code. What it shows you is that the posterior distribution for theta, which is this solid line here, is going to lie somewhere between the scaled likelihood and the prior. The prior distribution is, in this particular case, the prior distribution is this one here, right? And rather, this is the likelihood, sorry, this is the scaled likelihood, and we've got the prior distribution here. The posterior is going to be a compromise between the prior and the likelihood. Okay, so this is a very important idea that I'm going to unpack for you in great detail in the coming lectures. Well, this is the first intuition on the relationship between the likelihood and the prior. The prior is actually going to modulate your posterior distribution, right? The more precise your prior is going to be, the more the posterior distribution will drift towards the prior, right? And intuitively, this makes a lot of sense too, right? If you have a lot of knowledge about a particular problem and you get a new data set, that new data point, right, is not going to shift your belief much because you have a lot of prior knowledge about the problem. But if you know nothing about your problem and you get some data, that data will shift your belief about that the particular problem that you're studying. Okay? This happens in day-to-day life as well, right? Okay, and this is just another visualization of what I just showed you. We can basically see that the posterior is going to lie somewhere between the prior and the likelihood in this case. Okay. All right, so we've seen a simple example of how we can derive the posterior given some data in the simple binomial case. And what I showed you is that the posterior that we got actually belongs to the same family of distributions that the prior belongs to. How is that the case? How did that happen? Well, if you look at the posterior here, this posterior, these posteriors here, they all have the same form of the beta distribution kernel, right? If you go back to the beta distribution, what did it look like, right? this beta distribution kernel is the form that we are seeing in the posterior. So the posterior is just like the prior. It has the same form. So it belongs to the same family of distributions, namely the beta distribution. And that's why we say that this particular example of a binomial with a beta prior is called a conjugate case, because the prior and the posterior end up coming from the same family. Right? So this is a very important example which illustrates the key functionality that Bayes' rule gives you for figuring out the posterior. Right? So basically that's it. From now on we are going to be just computing this. Either we are going to do this analytically, we're going to do one more example of that, or we're going to do it computationally, and I will show you how that will work in the coming lectures. So the next lecture we'll look at another example of a paper pencil analysis like this one with a conjugate case involving the Poisson distribution and the gamma distribution.